Welcome. This is a video on computational geometry, part of the series of videos on advanced algorithms. In this video, we will talk about how to build efficiently KD trees and range trees using a technique called presorting, which is a common technique in computational geometry used in different settings where you have more than one dimension. To understand this video, one has to have a pretty firm grasp on the concepts of KD trees and range trees. So first, let's look at an algorithm that is not efficient, but is a straightforward implementation, the first attempt, a naive attempt at building a KD tree. Naturally, it's a divide and conquer algorithm corresponding to a binary structure of a KD tree. So here is the pseudo code of this simple algorithm. It gets P, the array of points, two-dimensional points, as an input. It gets the left index, the right index in this array, and it gets a flag, Boolean flag called odd, meaning whether this is an odd or an even level of the tree. So the first call to this function should be done with the parameters p1, n, where n is the number of elements in p, and true. So then, obviously, first we check, is this an odd level or an even level? Based on that, we either sort p on the x-coordinate or sort p on the y-coordinate, because that's how we want to divide points into two parts. We get the index of the middle point, and then we check whether this is a bottom of the recursion. So if L is equal to R, we have only one point, so we create a leaf node with that point. Otherwise, we either split according to the, we either put the splitting value in the internal node, which is either X value or Y value, depending on the level we are at, and that is the X or Y value of this element in the middle of the sorted order. So we create this internal node, and then we recursively build the left subtree on the containing all the points starting from L and up to V, including V, and then we build the right subtree containing all the points starting from V plus 1 up to R, and we flip the Boolean flag to show that now we go to the next level. And then we return the root. It's an obvious, simple implementation. The problem is that it's not efficient. So if one has to analyze the running time of this algorithm, the easiest way to do that is to write a recurrence for the running time, which will look something like this, that the running time of the algorithm on the array of size n will be, in general, if it's not the base case, will be equal to two times the running time of the algorithm on the array of the length that is twice shorter than n, plus all the rest here, and all the rest is dominated by this sorting, which is sorting the array of size n, so that's n log n. So this means that the running time, if we solve this recurrence, it turns out to be n log squared n. So we solved this recurrence on the blackboard in one of the lectures. It's a little bit difficult recurrence to solve because it does not fall into the cases of the master method, so one has to do it sort of by hand. Anyway, you get n log squared n, which is not the most efficient way to do that. So the goal is to drop this square and to just have an algorithm that runs in n log n, and that's what we will do. So here is a more efficient version of the build KD tree procedure that uses the idea of presorting. What the procedure gets as parameters are two arrays. One is what I call an X, capital X array, and another is a capital Y array. Both of these arrays are arrays of points. The only difference is that one is sorted on X coordinate, another is sorted on Y coordinate, but they contain the same, exactly the same set of points. And then the same auth parameter. So the pseudocode is here. First we check if the size of the array is 1, then we know that it's just 1 point, so we create a leaf node containing that point. Otherwise, here is a piece of code for the case when we are at the odd level, the level where we split according to the X coordinate. We compute the index of the point in the middle of the array. Then here we allocate 4 arrays: X left, X right, Y left, Y right. And these are the point arrays, new point arrays of size half of the original size. We just copy the first half of the array, of the X array, from 1 to V to XL. We copy all the elements from the second half of the X array to XR, so starting from V plus 1 up to X length. And then what we do is we pick elements from the Y array in the order of the Y array, and then we see for each element if the element belongs to the left subproblem or the right subproblem. So it's important to know that here I'm looking at the X coordinate in the Y array. So look at each point and see, look at its X coordinate and see if its X coordinate is smaller than this dividing line, the coordinate of the dividing line, then we append it to YL. Otherwise, we append it to YR. And so after this loop, which obviously takes linear time, what we have is 2 arrays YL and YR, where they are still sorted because both of them contain just a subset of points from Y in exactly the same order as they were originally in the array Y. And also we know that all the points in YL belong to the left subproblem we checked for each of the points. Then we can create a new root and build recursive the left subtree and the right subtree, passing these 2 sorted arrays as parameters and flipping the odd flag. And then there is also a corresponding piece of code where everything is the same, but if the level is not odd, we do the same as we did for Y, we do it for X. So we copy Y arrays and we select from the X array in this part. So what is now the running time of this algorithm? Well, we can see that we can write it as a recurrence. We still have the same part where we recursively solve 2 subproblems of half the size of the original problem. But the rest of it is linear. So the copying here is linear. Selecting from the y into YL and YR is also linear. So all of that is linear. So instead of n log n, as we had in the previous example, now we have only n, and that is obviously solves to the famous n log n. This uses the presorting idea that is used a lot in computational geometry. So for example, we could very easily modify this into an algorithm for building range trees. So the only thing that we would need to do is we would not need this odd thing here. So it would be a build, let's say build tree called, and then there would not be anything about the oddness of the level. And then we would not have all this part, right? We always build the main tree, and then the main change would be that whenever we build a node, we also build the associated structure of that node, which would be something like build 1D range tree, right? Which is more or less binary search tree on the points contained in Y. Right? It's containing all the points in Y. And so this part can be easily implemented in linear time. If you have a sorted array in Y, you can build up with a simple divide and conquer algorithm a binary search tree or one-dimensional range tree in linear time on that. So that time would be still linear, everything else would be linear using the same pre-sorting idea, and the recurrence would be the same, and we would have n log n algorithm to build range trees. We also saw the same technique of pre-sorting used, for example, in closest pair algorithm, divide and conquer closest pair algorithm, where exactly the same, we had exactly the same situation where in the combined step of our divide and conquer algorithm, we needed a set of elements sorted on Y in our subproblem, and so for that we can use the idea of pre-sorting to avoid sorting and instead just select elements from the already sorted array. So now let's look at an example of how the pre-sorting basically works in the divide phase of a divide and conquer algorithm that uses these two sorted arrays. So here we have two sorted arrays of points, two-dimensional points, each specified by the x and y coordinates. So this is the x array sorted on x. So I showed it in red, the x coordinates. As you can see, they are sorted. And here in the y array, we have exactly the same set of points, just sorted on y. So now I show in red the y coordinates, and you can see that they are sorted. And these are exactly the same points. So then in the main body of the algorithm, let's say this is a KD tree building algorithm, and let's say we pick as a pivot, we pick this element. So this is our V element, so V is 3 in this case, and so everything that has x coordinates smaller or equal than 5 belong to the left subproblem. Everything that has coordinates x coordinates larger than 5 belong to the right subproblem. So then obviously the we immediately have XL, right? And we have YXR. Then we have the for loop that goes through the Y array, and we build Y L and YR. Right? We just go through the array, through the Y array, and in linear time, just going once through that array, we pick the elements and see where do we have to append each of the elements, either to YL or YR. So 6, 1 has X coordinate that is larger than 5, 6, so it goes to YR. 6, 1. Then 3, 2 has X coordinate that is smaller than 5, so it belongs to the left subproblem, so we put it here. And 9, 3 is larger. 9 is larger than 5, so it goes here. 9, 3. This goes again here, because 8 is larger than 5. 8, 4. And then 5 is equal to 5, so this goes here. And 2 is smaller than 5, so it goes here. And so after this linear procedure, we have 2 sorted arrays on Y, as you can see, YL and YR. And YL contains exactly the same points as XL. And YR contains exactly the same points as XR.